But let's get this titled here. This is chapter 22, and it's called Gauss's Law. And Gauss's Law is great. Gauss's Law is going to impress your friends. Right? They're going to say what you're working on. You're going to say Gauss's Law. You go, oh, what's that? And you go, well, it's this. Right? Hold it up and show them. That's the kind of stuff we do in my physics class, right? We do Gauss's Law. Gauss's Law says this. Charges can't hide. Well, they can't. We'll see they actually can't hide sometimes. But for the most part, charges can't hide. Here's a charge. If I sample the electric field out here, what am I going to find? There's a charge somewhere, right? I know it because I can see there's an electric field here. What about over here? What about over here? And you go, charge. I'm found out. I've got an electric field just everywhere. There's no way in hiding it. If we look at an electric field at some location surrounding this charge, what do we say the magnitude of the electric field would be? We said it's kq over r squared. And why is that? And we said that's the way nature works. Okay, that's our starting point for electric forces. That's just how nature works. You get an electric field, that's k2 over r squared. But what Gauss realized, and Maxwell also realized in putting together some of these theorems, I think it's Maxwell who, I don't forget. What he realized was this. If we draw a boundary around that charge, and we measure electric fields along that boundary, what does it tell us? Charges can't hide, right? What do we know by sampling the electric field around this region? There's a charge inside somewhere. I know it. There's got to be a charge inside because why?
Because the electric field.
Everywhere I look along that surface, where's the electric field? Pointing out. I can't have the electric field pointing out from a region without having some kind of a source for the electric field. There's got to be a charge inside there somewhere. And what this integration is telling us is the Q is what is called enclosed charge. There's a charge enclosed in here somewhere. I know it. I can tell from the way the E field is configured. This side is integrating the electric field along the area, and the area here makes up what's called a Gaussian surface. So in our example we have right here, what's our Gaussian surface? Yeah, it's this sphere. So we made this spherical shell around this charge. That's our Gaussian surface. And all we have to do is carry out that integration, and we're going to know how much charge is present inside. Okay. It says if I go around an enclosed circle, and that's what this is saying. That little circle on the integration means what? It's closed. Now for a volume, a closed surface means that the surface completely wraps itself around. So there's no gaps in our net. What we've got is we're going to integrate area all the way around. Well, what would the area be equal to? 4 pi r squared. And what happens if I take the electric field and multiply by the area? The r squareds cancel out. Why does Gauss's law work? Well, because the electric field drops off like 1 over r squared, and the surface area is increased like r squared, and the two effects cancel. And it says that I could draw a surface out here, I could draw a surface in here, I could draw a really big surface over here. But no matter where I draw the surface, E times A is still going to be equal to 4 pi k times the enclosed charge. Okay? There's no way around it. So that's an easier version of thinking of Gauss's law. Now this only really works if what?
It's a sphere.
If the if it's a sphere. If I have spherical symmetry, then I can just say, what's the E field? The E field's uniform. So the E field here is the same as the E field here, same here, here. And so I can just write down a formula for the E field, write down a formula for the area, and say it's got to be this. Gauss's law takes this a few steps farther. What it says is, it doesn't matter what the shape is. I can make a crazy shaped surface if I really want to carry out that integration. And I'm guaranteed that the integration will still add up to 4 pi k times whatever the enclosed charge is. Okay, it's just guaranteed. I can change the shape of this however I want. Now to carry that integration, we have to have some agreements on a couple of things here. I guess we already are clear about the electric field. How the electric field is oriented. What is an area vector? Now I've seen line vectors, right? I've seen vectors that are like, if I had a line vector, what would its magnitude be? Be the length of the line. And what direction would it be pointing in?
Parallel.
Well, something parallel to the line. But what if you have an area?
It's perpendicular.
How do you decide what direction? I know what the magnitude is. I just calculate the area. But how do you decide what direction an area is pointing?
It's perpendicular.
Yeah, use a perpendicular. And at first that seems a little weird, okay? But what happens is, if we pick something that's perpendicular to the surface, that uniquely defines the orientation of the plane. If I have an area vector that's like this, how is the surface configured? Like that, right? It's got to be perfect. There's no question. It's not like, well, it could be here. It's got to be like this. Okay, the area vector is pointing over here. The area itself must be oriented this way. So, and again, there's this coin toss. Same thing as with the line vector. You know, I could have defined the vector this way or this way. So, area vectors can be defined in either direction. So let's step back to our Gaussian surface. How do we want to define the area vector along a closed spherical shell? We could define the area vector in toward the center, or we could define it outwards. Which way do you guys want to define it? Outwards. Okay, good. You're following the convention that mathematicians have come up with. So if I have a surface enclosing a volume, the official direction of the area vector is pointing out away from that volume. So it says that I've got E fields that are pointing outwards. I've got area vectors that are pointing outwards. What makes it a dA vector? I just make it little, okay? So I take just a little bit of area at a time, but it's still got an orientation to it. So that's what this integration is. Now, usually, you know, when students look at this formula, they go, wow, the left side of that formula, that's going to be the really difficult side to work with. Now, the right side looks easy. It's not true. It's the left side that's easy. Because the left side turned into what? E times A. So when I integrate this, we're only going to be integrating it in simple circumstances. Okay, the general theorem says I could make crazy, crazy shapes. We're not going to do that because why? Yeah, we're learning Gauss's law as a way to simplify our lives, not make it more difficult. So we're only going to integrate this under the simplest of circumstances. This is the harder part. And let's take a look at an example, and we'll see why. But that's the idea with Gauss's law. I have to be clear on area vectors. Usually the left side of Gauss's law is a trivial integration. Those are the best, right? You show your friends, wow, I am doing these kind of integrations. You go, yeah, but it just takes 5 seconds. It's a 5-second interval. All right. I have a uniformly charged sphere. It is not a point charge. What's the electric field? Actually, we can pick any point we want. We'll pick something along here. I'm going to pick a point right there. What's the magnitude of the electric field at that point? The sphere, let me tell you this. I guess we want some information here. The sphere has a radius of big R. And it has a combined Q of Q. And it's uniformly distributed.
KQ over R.
What's the E field at point A?
KQ over R.
And Coulomb's law would actually say, or the force, what we did in 21, in chapter 21 would say, what do we have to do at point A? We have to look at all the contributions from every little piece of this sphere.
which would mean what? Breaking it up into lots of little d volumes and integrating across the whole thing. Do we want to do that? No, not routinely. Okay, so sure, it's a challenge sometime, but Gauss's law gives us a shortcut. Gauss's law says, look, what we know is that for any individual charge, we can play this Gauss's law game of, I enclose this with a Gaussian surface. I'm not going to enclose it with just any Gaussian surface. I'm going to pick a surface that mimics the symmetry that I have in my charge distribution. What shape is my charge distribution? It's a sphere. I'm going to surround that with a spherically shaped surface. What does symmetry in the problem guarantee about what's the E field here, compared with the E field here, compared with the E field here, compared with the E field here? What can we say?
The same.
Same magnitude. And how are those E fields oriented with the area vector along the surface? If I sample the electric field here,
They're
how does it
parallel.
compare with dA? It's parallel. Okay. So what that says for Gauss's law is I can integrate that left side. Now the left side of Gauss's law is called the electric field flux, or just the electric, yeah, I guess we should say field, flux. Okay. So that's an electric field flux calculation. And I know that flux a lot of times gets treated as a density, but flux really has two different definitions. So right now it's not a density, it's a bunch of field lines multiplied by an area. Okay. So, and the way I do that calculation is, first of all, what's E dot dA along the surface? Yeah, they're parallel, so I can drop the vector sign and say it's the same thing as EDA. That's the first step. So I drop the vector signs of the dot product and say, look, they're just lined up. It's just going to be EDA. And then the next step would be, let's pull E outside. Why are we pulling E outside? It's constant. It's just a magnitude now that we're working with, and that means it's just going to be a constant value. And that's got to be true because of symmetry. There's nothing that distinguishes this point from this one relative to what the charge distribution looks like. That's the idea. So I got these two vectors. They line right up. I drop the vector sign. I can pull the E out because it's constant. Now I'm doing a surface integration over a spherical shell. What's the surface of that shell? 4 pi r squared. So we're going to write this as, but is it 4 pi big R squared? No, we need another R. So what we're going to do is we're going to define a second R. This is little r. Who's our constant? Who's the variable? Big R is the constant. Little r is the variable. So, and I have to be clear that the Gaussian surface is at the location little r from the center. So the left side's done. What are we going to do on the right side? Well, the right side of this says it's got to be equal to 4 pi kq, where q is the enclosed charge. It has to be enclosed in the surface. How much of this is enclosed? All of it. So all of this is generating electric field, and the electric field that I'm measuring along the surface is due to all of this charge enclosed to the side. So we're going to write this as
4 pi cancels out.
4 pi kq. What do I get for an electric field around a uniform sphere of charge?
KQ over R squared.
Yeah, I'm going to get kq over r squared. Okay. So it doesn't just apply for point charges. We can extend that now. Gauss's law says it's not just a point charge that's kq over r squared for the E field. It's anything with a spherically symmetric distribution. Now, what if it wasn't spherically symmetric? What if the charge density here was higher than the charge density over here? Does Gauss's law still apply? Yeah, it does. Do I still want to do that integration? No, I don't. Okay, because now the E field won't be uniform, and we'll get stuck at this step right here. Right? I can't pull the E outside. I can't complete the integration on this side. It gets to be more. complicated enough that I'm going to go back and do a direct integration instead. But for a lot of symmetry, Gauss's law works really well. Saves us a lot of time. So now in the book, they've already started moving over and using, let's go back and talk about this. When we first introduced the electric force, we said the electric force between two charges, K, Q1, Q2 over R squared, they have started doing what? They introduced something called 1 over 4 pi epsilon naught, which I have a hard time understanding why we want to do that. But we do. Now, making this switch over makes Gauss's law look like this. It makes Gauss's law look like 1 over epsilon naught times Q. And some people point to that and go, see, it's such a simplification. I disagree. I think this is still the easier way to do it. I'm willing to write Gauss's law with 4 pi k on it. Okay, and you guys just need to be aware. The book's going to shift over and pretty much exclusively use epsilon naught. I'm going to keep using k. There's really only one electromagnetic force in nature. You only need one force constant. So, but that's how you convert back and forth. So, epsilon naught is equal, in the one that's used in the book, 1 over 4 pi k. And the k that I'm using is 1 over 4 pi epsilon naught. Okay, that's the conversion between the two. All right, this is great. I've got the electric field figured out outside. What's the electric field right there?
Zero. Oh.
Let's see, I start at point A, I'm measuring the electric field, it looks like KQ over R squared, little r is a variable. I'm stepping towards the sphere, what's happening to the magnitude of the E field? It's going up, right? Just like if it's a point charge. But wait, it's not a point charge, at some point I hit the surface. If I continue into this charge distribution, measuring the E field, by the time I get to the center, what will the E field be?
0.
Yeah, and why 0?
It's the center.
I'm going to get complete cancellation. Now that's not the same thing. If we had a point charge, what would happen to the electric field as we got closer and closer?
Go
It would
stronger.
approach infinity, right? What's the E field at the center of a point charge? You go, well, the point charge goes infinitely large. Now what happens in reality is there are no point charges, right? So charges always have a little bit of distribution to them. And at some point, as you're getting closer and closer to the point charge, at some point you hit the boundary of that distribution of charge. I mean, if it's an electron or a proton, there's a distribution of charge that's present. So, in any case, some point we're going to have to hit this. If we do have a spherical distribution of charge, once we get to the center of back, the E field has to be 0 because why?
Cancel.
Yeah, cancellation. We're getting canceling effects now. So all the way up to the surface, everybody in here kind of agreed the electric field will be in that direction. But once you step inside, they're disagreeing. No, I don't want it in that direction. So we're going to get cancellations. Let me go back and pick up one more item here. What do you think about Gauss's law? Would that work for gravity? Why would Gauss's law work or not work for gravity? How does the force of gravity work? How do gravitational fields work around point masses?
Will work.
And it's gmr squared. No, actually, Gauss's law works great for gravity. It's not a directional effect. The important thing we need for Gauss's law is a force or a field that behaves like 1 over r squared, and gravity meets that requirement. So since gravity also behaves like 1 over r squared, we could write down Gauss's law for gravity. What would that look like? Gravitational field integrated over some Gaussian surface is equal to 4 pi
G
times m, where m is what? The enclosed mass. Okay, so everything we say about this charged sphere applies for measuring Earth's gravitational field if we drilled a hole and went to the center of the planet. going to work the same way. They're both 1 over r squared fields. So let's do that. Let's see what happens. If we look inside this spherical distribution of charge. So where is big R now? Well, big R is a constant. It's still the radius of the sphere. Where is little r? Well, let's just pick a point. Yeah, let's not go all the way to the center yet. What we'll do is measure from the center out to here. That's little r. So what happens is this. We've already done little r is bigger than the radius of the sphere. That's called outside the sphere. And that gave us an E field that was KQ over r squared. Now we're going to look at what about variable little r is less than, that's called inside the sphere. So we want to find out what the electric field is going to be. So let's see. Let's get Gauss's law set up here. Those charges. Right. Let's see. What happens on this side when I do this integration with a Gaussian surface, which is now where? Where's my Gaussian surface? It's inside. So it's got to include that point where I want to do the measurement. So that's my new Gaussian surface right here. It has a radius of little r, but the radius is inside now. So when I carry this integration out, what do I get? Okay, how long did that integration take? 5 seconds, right? So it's just E times A again. Everything we said before still applies. The electric field is going to be pointing away from this region. And the area vectors are going to be parallel. So we just run through the same set of steps, and the left side just integrates out simply, just as before. Okay, I'm looking pretty good here, except that, ooh, what's Q? If Q is not the same, how much charge do we have enclosed in the Gaussian surface? Only a fraction of the total volume. Okay. It's uniform, so what we can do is we'll do a ratio here. To get the enclosed charge, what we'll say is charge enclosed over the total charge is equal to volume enclosed over the total volume. Now we can get away with that because the charge density is uniform. So this would say enclosed charge divided by total charge, the fraction of charge that's enclosed now, is equal to how much volume have we enclosed? It is 4 pi, 4/3 pi, r cubed, which are enclosed charge. Little r. Yeah, because all we're including now is this much charge. The charge that's outside, why are we leaving that out? It's giving us perfect cancellation. So the charges out here are the ones that any location inside that outer charge, all of the effects from the outer charges are canceling. So we've ignored everything that's canceling out, and we're just focused now on how much charge is working together to give us our E field in that direction. So this is going to be 4/3 pi r to the third, and what's in my denominator? That's the total volume, which would be what? Yeah, that's it. So this is going to be the 4/3 pi big R squared. And that says that enclosed charge is equal to this fraction of the total charge. It's equal to little r cubed over big R cubed. Okay, quick check here. If I'm halfway between center and surface, how much of the charge have we enclosed? I'm halfway. So how much charge has been enclosed? 1/8. Good. Why is it 1/8? Because it's cubed, right? If you take a volume, you take some sphere and measure its volume, and you take a sphere with half the radius or half the diameter, how do the volumes compare? Yeah, it's a ratio of 8 to 1. You know, this one was 8 times the volume. All right, quick check. Can't pass up on this one. Okay, here is the sun. How much bigger than the Earth is the sun? And if you read this, they'll say it's 100 times bigger.
No.
Well, 100 times bigger in what? Diameter. Now, I don't want to think diameter, I want to think volume, right? If I'm thinking how big an object is, I want to think volume. So if you could stack 100 Earths across, how many would it take to fill the whole volume? It'd be 100 cubed, which would be 1,000,000. Okay, that's a big difference between saying the sun's 100 times bigger than the Earth versus the sun's 1,000,000 times bigger than the Earth. And in terms of volume, that's 100, it's 1,000,000 times bigger, not 100. Okay, so when you hear that on a TV show, or the sun is 100 times bigger, make sure you get that correct. Make sure everybody in the room knows that that's